Have you ever wondered how fluids behave in pipes? How do pipes work? What pressure drop is needed to drive the flow? Well, today we are talking about the viscous flow in ducts. This topic is very important to us as an engineers. Piping systems are encouraged in almost every engineering design and thus have been studied extensively. The basic piping problem is this: given the pipe geometry and its added components such as fittings, valves, vent, and diffusers, plus the desired flow rate and fluid properties. To know the solution to one of the most important problems in fluid engineering as flow in ducts with various velocities, various fluids, and various duct shapes, allows to realize and to analyze the different forms in which a fluid can behave and in turn to understand the necessary parameters for the construction of pipes and ducts according to the special needs that appear. For this reason, we will start by talking about the Reynolds number regimes. During our part of a study, a great diversity of tools and basic equations have been available to solve some of the problems. However, there is still no general analysis for the movement of fluids. There is a lot of theory available if we neglect such important effects as viscosity and compressibility, but there is no general theory. The reason is that a profound and vexing change in fluid behavior occurs at moderate Reynolds numbers. The fluid ceases being smooth, steady, or laminar and becomes influctuating and agitated or turbulent. The changeover is called transition to turbulence. The transition depends on many effects, such as roughness or fluctuation in the inlet stream, but the primary parameter is the Reynolds number. As we can see in these images, there are three regimens of viscous flow. First, we can see the laminar flow. The second is transition and intermediate. And finally, we can have a three, that is a turbulent flow at high. If the flow is laminar, there may be occasional natural disturbances that damp out quickly. If transition is occurring, there will be sharp bursts of indeterminate of turbulence fluctuation. As increasing the Reynolds number causes a breakdown on instability of laminar motion and insufficiently large Raymond. The flow will fluctuate continually and is termed fully turbulent. The fluctuation typically ranging from 1 to 20% of average velocity trajectories joined by the liquid sheet. The higher Reynolds number turbulence flow is unsteady and irregular, but when averaged over time is steady and predictable.
Okay, how did turbulence form inside the pipe? The laminar parabolic profile became unstable and began to form puffs of intense turbulence. Well, it is known that a puff has a front that moves at great speed and a rear that turns out to be opposite. It moves slowly. This can be visualized better with this image. Okay, in the first and second part of the image, part A and part B, we can see a puff near the entrance. A puff, as I already said, represents turbulence. In the part C of the image, there is an irregular laminar turbulent interface. The puff becomes fully turbulent and very active with visible motion. In the last part of the image, the puff is less active. In the part D. Okay, In the primary parameter affecting transitions is the Reynolds number, expressed with this formula, where U is the average stream velocity and L is the width or transverse thickness of the tube, and V is the kinematic viscosity of the fluid, depending of what kind the fluid we work. The value of the Reynolds number allows to determine the type of motion that is occurring, represented in the following image. For example, in the range of 0 and 1, the motion is highly viscous laminar, creeping motion, and depending of the value of the Reynolds number, can a different classification. Turbulence can change the mean values of velocity, pressure, force, and so on dramatically. Hagen measured water flow in long brass pipes and deduced a pressure drop law. This is the formula. But Hagen didn't realize that the constant was proportional to the fluid viscosity, so that the formula broke down as Hagen increased Q beyond past the critical Reynolds number. And he stated that there must be a second mode of flow characterized by strong movements of water, for which pressure drop varies as the second power as the discharge. Okay, in this graphic is represented what Hagen meant, and we can see that the pressure drop varies linearly with V equals Q for A, up to about 1.1 feet per second, where there is a sharp change. Osborne-Reynolds showed that the change depends of this parameter. By introducing a diastric into a pipe flow, Reynolds could observe transitions and turbulence. There are now extensive theories and experimental of laminar flow instability that explain why a flow change to turbulence. Laminar flow theory is now well developed and many solutions are known. Therefore, most turbulent flow theory are semi-empirical.
Okay, in this part, I'm talking about the internal versus external viscous flows. First concept, both laminar and turbulent flow can be internal, that is confined by walls, or external and free. In this case, I'm talking about the internal flows. Internal flow is confined by walls, where the viscous region decreases to complete a flow. Internal flow in a long conduct is a picture that we show with three characteristics important. First, upward flow. Second, viscous ledger, and third, continuity requirement. And important parameters like linear pressure drop, entrance pressure drop, entrance length, and fully developed flow rate. In the part of equation, we have three equations. First, you find in this formula of the flow rate as it becomes the units, and arrange the velocity. In the second parameter, determine the Reynolds number and the impulse length and speed with this relation. And finally, we find the equation of the Reynolds number with the equation of Reynolds. In the part of purification, the maximum laminar and stretch number, we have important Reynolds critic and LE equal 1038 G. In a turbulent flow, the boundary layers grow faster, and LE is relatively shorter, and is determined by the following formula. And third, some values turbulent and trench length estimate are the relation of the Reynolds number at the second parameter. In this example, we have some dates and one incognite is entrance region. For the solution, first convert flux units in this part, and second determine arrange velocity with this formula. Third, determine the Reynolds number with the equation of Reynolds, and use a velocity of water in some tables in the book. For the conclusion, this value is greater than 4,000, therefore the flow is totally turbulent. And finally, and four, determine the entrance length with this relation, and actual tube has with the relation L on D. For apply these values in this equation, for the conclusion, the percent is very small, so we say that flow is fully developed. One important fact is usually 90 diameters may seem long, but in the flow typical application value the relation L on D of 1,000 diameters or more. Second, the entrance effect may be neglected. Third, the analysis for fully developed flow. And finally, both laminar and turbulent flows apply in this part road walls and not circular cross sections, and correspond in an aerodynamic tunnel. The short length is useful is when to have a non-viscous curve, when it's necessary to have the lowest possible viscosity for the simulation on a free current conditions. And third, the length is much smaller in the relation with development of the flow.
Head loss, the friction factor. It is the loss pressure that occurs in a fluid due to the friction of the particles and against the walls of the pipe that lets them. For that reason, it's important to understand that overall head loss in a pipe is affected by a number of factors, which include the viscosity of the fluid, the size of internal pipe diameter, the internal roughness of the inner surface of the pipe, the change in elevation between the ends of the pipe, and length of the pipe along which a fluid travels. For that reason, in this part, we will analyze the formula to generate and estimate. When applying pipe flow formulas to particular problems, it's customary to use a control volume analysis. Consider incompressibly steady flow between section 1 and section 2 of the inclined constant area pipe. These equations can reduce to head loss versus pressure drop and elevation change. Other important thing is the pipe head loss equals the change in the sum of pressure and gravity head, that is, the change in head of the hydraulic red line, HGL. We find that the head loss is also related wall shear stress. Note that, regardless of whether the pipe is horizontal side, the head loss is proportional to the wall shear stress. Now it's important to do a question about how should we correlate the head loss for the pipe flow problems? For that reason, it's necessary to talk about Julius Viscous, who published the first modern textbook of hydrodynamics, where he proposed the following correlation. And in the other side, we can see this equation is an alternative from the friction factor. In other side, we can talk about the laminar fully developed pipe flow. Analytically, solutions can be really derived for the laminar flows, either circular or non-circular. Consider fully developed Poisson flow in a round pipe of diameter d or radius r. With wall shear stress known, the Poisson flow friction factor is easily determined, like this equation. And finally, it's important to say that in laminar flow, the pipe friction factor decreases inversely with Reynolds number.
Finally, we can say that all these topics will help us in the future to determine important aspects to understand the behavior of fluids. Thanks.